In 5.2, we're going to talk about definite integrals. So we've done indefinite integrals in sections 4.9 and the beginning of 5.5. So we're starting with a new type of integrals. Before we get there, we need to talk about what we already know about the area under a curve and how it can be approximated in Riemann sums. And we haven't yet talked about what happened if the curve dips below the x-axis. How are we going to account for this area underneath the curve? So how do the Riemann sums work in cases like that? So that's what we're going to discuss first. Okay, so in example 1, we're looking at a function that is both positive and negative. It's just a line, and the equation is 3 minus x, and we're looking at it over the interval 0 to 5. So we're going to approximate the following using right Riemann sums, find the net area between the curve and the x-axis. Okay, so with n equals 5, our delta x would be 5 minus 0 over 5 equals 1. Okay, so every 1 we're going to draw up to the curve, and then we're going to make our rectangles after we draw them, and every 1 we'll draw down to the curve if it's below. Okay, and it says write Riemann sums, and so write Riemann sums we'll use right endpoints. Okay, and so write Riemann sum and write Riemann sum. There we go. And so our rectangles, if we shade them in, will look like this. Now there's nothing to shade right here because it's just a line since that one is flat. Okay, so this would be our right Riemann sums with n equals 5, and the Riemann sums, we can do these by hand, we don't need sigma notation. Remember, they're going to take delta x times the y coordinate, and so we're going to use f of 1, f of 2, f of 3, f of 4, and f of 5 as the xk stars. So we have delta x, which is 1 times f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. Those are the right endpoints. So we're just going to plug them into the function. Now it's going to come out easy. We can just look at them and see them. We don't really need to plug in 1. 3 minus 1 is 2. You can see it's 2. So this is going to be 1 times 2 plus 1 plus 0 plus negative 1 plus negative 2. And so we're going to get 0, which probably didn't surprise you if you're taking a look at this. We have some things above the x-axis and things below the x-axis, and they're the same size. So we're getting a net area right now of 0. Now, that's actually not a good estimate of the true area, but it does get into the fact that regions that lie below the x-axis are going to have area that is defined to be negative, while regions that lie above the x-axis are going to have area that's defined to be positive. And so these are canceling out. There is quite a bit of error, and if I was a little more precise, I would have a non-zero number. I would see that this triangular region and this triangular region would cancel. It would leave me with this trapezoidal region, so it should be positive. But with this much error, having a wide 1 for my delta x is going to mean that we have considerable error right now. But we get the 0, so we get things canceling out, which is the idea that we want to emphasize here about the area under the curve. The curve even below the axis is going to be negative. Okay, and so we need to talk then about net area. We need to figure out what words we're going to use when we allow things to be positive or negative. So for distance and displacement, for example, displacement was signed, and so it allowed there to be negative, and distance is always positive. So in this picture, we've got the definition of net area, and regions that are above the x-axis are going to have positive areas, and regions below the x-axis are going to have negative areas. So if I consider the region bounded by this graph, the net area is the sum of all of these areas, the ones that are above minus the ones that are below, because these are negative, right? And so they're going to cancel out. So the net area is going to be a signed area. It's going to be signed because there are going to be some positive values and some negative values. So net area is signed area. Okay, so it allows for those negative regions below the x-axis. If we want not signed area, we just call it total area. So we'll just make that as a note, total area. is the phrase that we'll use if we add up the absolute values. So absolute value of all area regions, and add them up. After you take the absolute values, it would be all positive sum. Okay, not the absolute value of the total, but the absolute value of each individual piece. So sum of absolute values. Let's say that instead. So total area is the sum of the absolute values of the areas of the individual regions. So just for contrast, we'll talk more about total area later, but those are the two types of area that we're going to be talking about. Net area, signed, corresponds with our idea of displacement. Total area, always positive, corresponds with our idea of distance. Okay. So this is where calculus steps in and we bridge the gap between section 4.9 and 5.1. Okay, so this means that the number of rectangles in our Riemann sums is linked to the fixed width of those rectangles, and which in turn has a relationship with the area. So as n, the number of rectangles approaches infinity, delta x, which is b minus a over n, so delta x is going to be the limit as n approaches infinity of b minus a over n. That's a constant on top, b minus a. And so n gets infinitely large. So as the denominator gets infinitely large, means that delta x itself is going to 0. Because it's got a constant on the top and an infinitely large value in the denominator. And therefore, any Riemann sum, whether it's left, right, or mid, doesn't matter, approaches the actual area. Approaches the net area. Because we do need to allow for that signed area. So any Riemann sum is going to approach net area. Okay? So you can see the net area by the Riemann sum, where there are 75 rectangles versus this is a graph of the actual area as you allow the n number to go infinite instead of just 75. So we have a lot more, no rectangles are shown right here because there are infinitely many of them. And so it's going to be the actual area. Okay, so in the formal definition of our definite integral, notice that we are going back to the integral symbol. There are a few additions here. There are bounds on the interval. So we have those which are new. Those bounds are our upper bound and our lower bound. So our upper bound b, it's also the upper bound of the interval, right? AB is the interval. That's where the upper bound and lower bound come from. It's the upper bound and the lower bound. And it's still the integral of the integrand dx. The integrand is still the function that we were working with. For the k values in our summation, k equals 1 is just the starting value, and n is the number of iterations. Or the number of dividers in the subintervals. Number of divisions, I'll call it for short, number of divisions. And xk star is just the start of the interval. Does not correspond with a, it's just saying that if I start at the first interval, I'll be able to continue until I get to the second subinterval, and the third subinterval, and so forth. Okay, so these two things are going to be equal. That's how we're going to define what a definite integral is. It's going to be defined as equal to this Riemann sum. So we already know how to do the Riemann sum. The definite integral is when we do the Riemann sum as we let that delta x approach 0. So remember up here, delta x approach 0, that's how I define what a definite integral is. Okay, now how do we evaluate them? So look at the next page. So if I consider this example, find the net area using integration. Okay. We're going to start with the notation from the previous page that says that the integral between the lower bound and the upper bound, so 0 to 5, of the function 3 minus x dx should be equal to the limit as delta x gets closer to 0, delta gets closer to 0, of the sum from k equals 1 to n of delta x. So hold on, let's find delta x for this one again. So remember that delta x was 5 minus 0 over n. N is not 5 anymore, it's n. So I'm going to keep it as 5 over n. Times the function value. So it's going to be 3 minus x. Now, a is 0. And we can use xk star as anything because we're going to let these go infinite. So we're going to choose the simplest, which was the right. And that was just k. And so I'm going to have a plus k delta x. So that's our 5 over n. Okay. So to simplify this, we're looking at that limit as that change goes to 0 of the sum k equals 1 to n of 5 over n times 3 minus 5k over n. Now, we are, instead of actually doing a limit, and because if I had a limit, I would need to figure out this sum analytically, I'm going to do the limit numerically. If I do the limit numerically, I'm just going to pick bigger and bigger values of n, which are going to force that change to become small. So we're going to go to Desmos, and I already typed it, but again, you know how to enter a sum, and I have the sum right here, k equals 1 to n, and exactly what we had on paper right there, 5 over n, 3 minus 5k over n. I'm going to add a slider for n, and we're going to just increase the value of n and watch what happens to the sum. So, you might as well do 10, 100, 1,000, 10,000, 100,000. Let's see, what is happening is it's not changing much anymore. Yes, I've probably reached overflow, but it's really approaching 2.499. I think it's approaching 2.5. And so that's what we're going to guess, is that these are approaching, we think, 2.5. And we did that numerically. There are by hand ways to do it analytically, but I would then need to use distribute this, use the by hand ways to figure out what's happening to n. And we're going to focus on some other techniques. So numerical sounds like a kind of fine way to approximate these. It looks like it's going to 2.5. Okay. So what advantage does the integration method have over Riemann sum method? Well, depending on what we have for n, if n is too small, we have a lot of error. So we can get the exact area without having to worry about large error. Now, I don't yet have a way of proving that this is the exact value, and we're going to work on that as we continue this section in the next section. All right. Taking a look at the next page, using geometry to evaluate integrals. Now, I just want to mention this one could be done geometrically as well, and we can confirm that we actually do get the 2.5. So let's talk about it geometrically. So geometrically for this one, since I have these two triangles, I can find the area that way. And so the area of the first one is 1/2 base is 3, height is 3, plus the area of the second one is 1/2 base is 2, height is -2. So this is going to be 9 divided by 2, so 4.5 minus 2, and so I do get 2.5. So that's the geometric way of getting this one. Keep in mind that this portion down here is negative, whereas the portion up here was positive, and so that's why we're getting that cancellation and getting the 2.5 for the net area. Okay, so we are seeing a little bit of a few different methods here so far of computing it.